and I'm from the Buddhi Academy. So today we'll see the last part of the chapter D and F block elements. So in our last video we have seen about the lanthanide series. So today we'll see about the actinide series and the last part of this chapter. Okay, now the actinide series it starts from actinoids. Okay, it includes actinoids and has 14 elements from thorium to lawrencium. Okay, including actinium. Okay, from thorium to lawrencium, it has 14 elements. Now, these are the symbols of the 14 elements and their electronic configuration along with their atomic and ionic radius. Now, the actinoids are radioactive elements, and the earlier members have relatively long half-lives. The later ones have half-life values ranging from a day to 3 minutes for lawrencium. Okay, now these actinoids are radioactive elements and they have a relatively long half-life. Okay, and later ones have a half-life values ranging from a day to 3 minutes. Later members could be prepared only in nanogram quantities. So all these molecules, they can be prepared in nanogram quantities only. Can't prepare them in high quantities. Okay, they are prepared in nanogram quantities. This fact renders their study more difficult. So here it is in nanogram quantities. Nanogram means very little quantity that you can prepare. So which makes it difficult to study, because to study any compound or any molecule, it should have at least 1 gram. Okay, but here we are preparing only nanograms, or the molecules can be prepared only in nanograms, which makes it very difficult for study. Now, the electronic configuration, all the actinides are believed to have electronic configuration of 7s2. So they have a common 7s2 filling up. Okay, and variable occupancies of 5f and 6d. So here 7s2 is completely fixed. Every molecule will have a 7s2. Now the variable occupancies are of 5f and 6d. For example, in transition series, first transition series, you have 4s as 4s2 as common, right? And 3d is the variable one, because in 3d electrons are being added up, right? 1, 2, 3, like that. As you go down, the number of electrons are added up in the d orbital. So d is a variable occupancy, whereas 4s2 is a fixed occupancy. Now here 7s2 is fixed there. So everywhere you can have a 7s2 orbital filled. Now occupancy, variable occupancies are of 5f and 6d. Here you can see 5f2 61, 5f3 61. So here 5f is the one which is filling up, okay, along with 6d. Now the 14 electrons are formally added to 5f. So here compared to 6d, 5f is rather filled completely. Okay, though not in thorium. Okay, there is an exception in thorium and actinium. Okay, in both these cases there are differentiation. Here thorium, you can see there is no 5f orbital, right? And whereas in protactinium, one electron from the 6d is transferred to 5f. Okay. Thorium is an exception where no 5f orbital is there. 5f orbital starts from protactinium. Okay, that is Pa orbitals and complete at lawrencium. Now, the irregularities in the electronic configuration of actinoids, like those in the lanthanoids, are related to stability. Now, why there is a irregularity in electronic configuration is basically because to attain the stability. Okay, just to attain stability, they show irregularities in the electronic configurations. Configuration of AM, CM are, where is AM and CM? Here. americium and curium. Here the electronic configuration again. Here 6d is there, whereas here 5f7. Now this 61 is because 5f7 is half filled. Why half filled? For f orbitals, total 14 electrons. 14 ka half is 7. So 7 is a half filled electronic configuration which is stable, right? So that's why curium, adding this one electron into 5f, what they did is they have taken that one electron into 60, which keeps the curium stable. Okay. Although 5f orbitals resemble the 4f orbitals in their angular part of wave function, they are not as buried as 4f orbitals, and hence 5f electrons can participate in bonding to a far greater extent. Now 4f orbitals are placed quite inside the orbitals, right? Because after 4f orbitals you have 5d and 6s. So it is inside. Whereas here 5f orbitals, it is not placed far inside because all these molecules, they don't have a 6d orbitals. You can see they only have 5f and 7s. So there will be like 5f and 7s. Okay, so here this 5f orbitals, the electrons in the 5f orbitals will be participating in bond formations, okay, compared to 4f orbitals which are buried inside. Now their ionic sizes, atomic and ionic sizes. The general trend in lanthanoids is observable in the actinoids as well. So whatever the ionic changes or radii changes occurs in lanthanoids, same you can observe in actinoids. Okay, there is a gradual decrease in the size of atoms or ions across the series. So what happens? There is a decrease in their size as you go across the series. Now this may be referred as actinoid contraction. So the same way lanthanoid contraction, here for actinoids it is actinoid contraction. Now the contraction is however greater from elements to element in this series. So actinoid contraction and lanthanoid contraction are similar. Okay, in lanthanoids it is lanthanoid contraction, in actinoids it is actinoid contraction. But here in actinoids, the power or greater the element, the actinoid contraction is greater from element to elements. As you go with along the series, as the elements go on increasing, the contraction also increases. Okay, resulting in poor shielding of 5f electrons. Now, next is the oxidation state. Now, oxidation state, there is a greater range of oxidation state which is in a part attributed to the fact that 5f, 60 and 7s levels are comparable energies, are of comparable energies. The known oxidation states of the molecules are given here. Okay, here also the oxidation can come up to +7. Okay, now the actinoid shows a general +3 oxidation state. So there is a general +3 oxidation state. Only for thorium it's an exception. Except the thorium, all the other molecules, they show a general +3 oxidation state. Now the elements in the first half of the series frequently exhibit higher oxidation states. So first half of the molecules, still americium, you can see they have a higher oxidation states. Now for example, maximum oxidation state increases from +4 to +4 in thorium to +5, +6 and +7. Right? +4 it starts from thorium. Then you have +6, +5, 6 and 7. Right? Now, respectively in potassium, uranium, neptunium, plutonium and americium. So as you go respectively in all these molecules, but decreases in succeeding elements. Okay, so till here, till plutonium you have +7 ka oxidation. Then you can see there is a decrease in the oxidation state as you go further. So actinoid resembles the lanthanoids in having more compounds in plus 3 state. So as I told you earlier, in lanthanoids, plus 3 is the common oxidation state. All the molecules, they possess a plus 3 oxidation state. So it resembles lanthanoids. Actinoids also have a common plus 3 oxidation state. Now, however, plus 3 and plus 4 ions tend to hydrolyze. So here, this plus 3 and plus 4, the oxidation states of plus 3 and plus 4, they can tend to hydrolyze. Hydrolyze means what? We can break them using water. Okay. Because the distribution of oxidation state among the actinoids is so uneven and so different from the former and later elements, it is unsatisfactory to review their chemistry in terms of oxidation state. So here you can see कि all these molecules, they show different oxidation states, right? It is not regular pattern. There is an irregularity that can be seen. This and their radioactivity. Both these concepts makes it difficult to study about these compounds, and using oxidation state to learn their chemistry using oxidation states is really difficult. Okay. Now next is the general characteristics and comparison with lanthanoids. Okay, let's compare these molecules with lanthanoids. The actinoid metals are very silvery in appearance but display a variety of structures. The structural variability is obtained due to irregularities in metallic radii, which are far greater than in lanthanoids. Now, actinoids, they are silver, they appear in silver color. Okay, they are silvery in appearance and display variety of structures. They show various structures. Another thing, this is because the structural variability, they show various structures because of their irregularities in metallic radii, because of their atomic and ionic radii. Okay, because of their radii, as I told you, the radius is not regular. There is an irregularity in the radius. So because of that, they show structural variability. And this structural variability is far greater than lanthanoids. Okay. Now, the actinoids are highly reactive metals. As I told you, they are radioactive, so they are highly reactive metals, especially when finely divided. Finely divided means when you convert them into fine powders. Now, the action of boiling water on them, for example, gives a mixture of oxide and hydride in combination with most non-metals, takes place at moderate temperature. Now, hydrochloric acid attacks all metals, but most are slightly affected by nitric acid, owing to the formation of protective oxide layers. Now, these are their reactivities. So, the molecules or the radioactive metals or the actinides, they react or they give mixtures of oxides and hydride and combine with most of the, they form oxides and hydrides, okay, and also combine with most of the non-metals, and this all these things takes place at moderate temperature, not in a high temperature, not in a low temperature. It takes place in a moderate temperature. What takes place in a moderate temperature? The formation of their compounds with non-metals and formation of hydrides and oxides. Okay. Now they react with hydrochloric acid. Okay. They also react with hydrochloric acid, but they show a very slight effect on nitric acid. So when we react these actinoids with nitric acid, they doesn't show, or they show very slight effect. Whereas with hydrochloric acid, they show a greater amount of changes. Now when we add nitric acid, they show slight, they doesn't affect much because of the formation of protective oxide layers. Okay, and with alkalis, they do not react. Now this part is their reactivity, how they react. This part is their reactivity. Now next is the magnetic properties. Okay, the magnetic properties of actinoids are more complex than those of lanthanoids. Now here, why the magnetic properties are more complicated than lanthanoids is basically because of their radioactivity. Now, although the variation in the magnetic susceptibility of actinoids with the number of unpaired 5F electron is roughly parallel to the corresponding results for lanthanoid, the latter have higher values. Here, you can compare the unpaired electrons of 5F electrons with their magnetic orientation similar to lanthanoids, but later you can see that the values are changing, and also with their radius and radioactivity you can't predict the higher ones. The next is it is evident from the behavior of actinoids that the ionization enthalpies of the early actinoids, though not accurately known, but are lower than the early lanthanoids. Okay, now the ionization enthalpy, as I told you, कि 4f orbitals, okay, to remove an electron from 4f orbitals is difficult than 5f orbitals, okay, because after 4f orbitals, okay, after 4f orbitals you have 5d and 6s. Right. So to remove an electron from 4f orbitals, you have to first remove electrons from 6s and 5d. So it is placed inside. So to remove an electron from here, it is difficult. Whereas for 5f, you only have, after that is 7s. And even though if there is 5f, 6d and 7s, 6d has only one electron intact. Here 5ds are almost filled. Okay. Here 6d has only one electron. So to remove electrons from 5f is rather easier than compared to 4f. So that's why the ionization enthalpy for actinoids, okay, is lower than the lanthanoids. Okay. This is why the ionization enthalpy of actinoids is lower than lanthanoids. Now, this is quite reasonable since it is to be ex, expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of the electrons, as I told you. Now, the 5f electrons will therefore be more effectively shielded from the nuclear charge than the 4f electrons of the corresponding lanthanides. Because the outer electrons are less firmly held, they are available for bonding in the actinides. Okay, same thing happens. So 4f, it is kept inside. So there is the shielding effect is more compared to 5f electrons. So hence the electrons removing from 4f electrons is rather easier than the rather difficult than the 5f. 5f is easier. That's why it is involved in the bond formations. Okay. Now, a comparison of the actinoids with the lanthanoids with respect to different characteristics as discussed above reveals the behavior similar to that of lanthanoids. Now, whatever we have discussed, there are certain similarities, right? Actinoids, they have some similarities with lanthanoids. But it is not evident until the second half of the actinoid series. Okay, only till first half you can see the similarity. For the second half of actinoid series, it is not that evident. Okay, it's not that applicable. Even the early actinoids resemble the lanthanoids in showing close similarities with each other and in gradual variation in properties which do not entail change in the oxidation state. Now, the lanthanoids are similar to the first half of the actinoids. Okay, there you can see there's some of similarities, but there is a gradual variation in the properties, not to in oxidation state. Okay, oxidation state, you can't compare them. Now, the lanthanoids and actinoid contractions have extended effects on the sizes and therefore the properties of the elements succeeding them in their respective periods. So there is lanthanoid and actinoid contraction, but as I told you, actinoid contraction, as you go with the series from element to element, it occurs in a greater extent. Okay. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present. So for as of now, lanthanoid contraction is more important because actinoids, half of the molecules study is not completed at present. So therefore, lanthanoid contraction is more important than actinoid. Okay. Now, here are some applications of D and F block elements. Now, iron and steel are the most important construction materials. As you know, iron and steel both are D block elements. So they are important in construction materials. Their production is based on the reduction of iron oxides and removal of impurities and addition of carbon and alloying metals such as chromium, manganese and nickel. Now how these iron and steel are produced? They are produced in on the base. They are produced on the reduction of iron oxides are reduced, the removal of impurities, the impurities are removed, and the addition of carbon and alloying metals. Now, which are the alloying metals that are used? That is chromium, manganese, and nickel. All these three are transition metals. Now, some compounds are manufactured for special purposes such as TiO, that is titanium oxide. Okay, for the pigment industries, and MnO2 for use of dry battery cells. Okay, now MnO2 is used for the dry battery cells as a electrolyte. Okay, now the battery industry also requires Zn and nickel cadmium. So there is a nickel cadmium battery, and in dry cell only, dry battery cell only, we use zinc as an anode. Okay, this you will learn in the electrochemistry chapter. Now the elements of group 11 are still worthy of being called as coinage metals, although gold and silver are restricted to collection items, and the contemporary UK copper coins are copper coated steels. Okay, so there are gold and silver which are also transition metals, and even copper coated coins which are used in UK still. Now the silver UK coins are a copper nickel alloy. Okay, those coins are made up of copper and nickel. Okay, now many of the metals and or their compounds are essential catalyst in chemical industry. So they can also be used as catalyst, okay, in chemical industries. Now vanadium pentoxide catalyzes the oxidation of sulfur dioxide in the manufacture of sulfuric acid. Now vanadium pentoxide can be used in the production of sulfuric acid as it can oxidize sulfur dioxide. Okay. Now titanium tetrachloride and aluminium and AlCH with AlCH3 thrice forms the basis of the Ziegler catalyst. So this is a catalyst. Here you can see titanium is used, which is a transition metal. Okay, it is used as a Ziegler catalyst, which is used for the manufacture of polythene. Okay, iron catalysts are used in the Haber processes. Now, iron catalysts are used in Haber processes for the production of ammonia. Now, nickel catalysts are used in hydrogenation of fats. Okay, in the Wacker process. Okay, these are the reactions that are um, carried out in various industries. Okay, and these are the catalysts that are used for this processes. Now, Wacker process here for oxidation of ethine to ethanol, a catalyst of palladium dichloride is used. Again, a nickel complex, nickel, platinum, and palladium are a common catalysts. Okay, so you can see nickel catalyst. Almost most of the catalysts are with nickel, platinum, or palladium. Okay. Now again, a nickel complex are useful in the polymerization of alkynes and the organic compound such as benzenes. The photographic industry relies on the special light sensitivity of AGBR. AGBR is your silver bromide. So these are the uses of or applications of D and F block elements. So we are done with the chapter. That's the last part. This was the last part that was remaining. Now, in today's class, we have seen about the actinoids, their electronic configuration, atomic and ionic radius, oxidations, their some of their general characteristics in comparison with lanthanoids, and some of the applications of D and F block elements. I hope you all have understood the chapters. Thank you for watching my video. Please do like, share, and subscribe to our channel.